Imagine an open ocean. The waves are large, perhaps 10 meters high, but consistent. Then, without warning, the sea in front of you seems to open up. A deep, dark trough appears where a wave crest should be. Moments later, a single, vertical wall of water erupts from the chasm, towering 2, even 3 times higher than any other wave on the water. This is not a tsunami, born from seismic upheaval miles below. This is a rogue wave, a spontaneous monster created on the surface, a freak of fluid dynamics that appears from nowhere, concentrates immense power into one peak, and vanishes just as quickly. It is one of the most terrifying and mysterious phenomena sailors can face. For centuries, mariners have passed down stories of these impossible waves. They spoke of ships sailing into what they called holes in the sea, only to be met by a nearly vertical wall of water that would rise up and break over their vessel with unimaginable force. These weren't just big waves. They were described as fundamentally different, a liquid cliff in the middle of the ocean. These tales were filled with awe and terror. They were the legends of the deep, whispered in ports from Europe to Asia. Experienced sailors swore they had seen them, lone mountains of water that defied all logic and expectation. But when these accounts reached the world of science, they were met with disbelief. To oceanographers and physicists of the 19th and 20th centuries, these stories were just that, stories. They were considered maritime myth, the exaggerations of sailors who had survived a bad storm and spun a taller tale. The math simply did not support their existence. According to the established scientific models, the distribution of wave heights in the open ocean follows a predictable pattern. While waves can combine and grow larger, the probability of a single wave reaching 3 times the height of its neighbors was considered infinitesimally small. It was an event so unlikely it would happen only once every 10,000 years. The sailors' accounts were dismissed as statistically impossible. Then came January 1, 1995. On the Dropner gas platform, a steel structure anchored in the notoriously rough North Sea, a storm was raging. The platform was equipped with a state-of-the-art laser sensor, a device designed to precisely measure the height of the waves crashing against its legs. And that day, it recorded the impossible. The data was unambiguous. The significant wave height, a term for the average of the highest third of the waves, was around 12 meters, or 40 feet. But in the middle of this chaotic sea, the laser sensor measured a single colossal peak. It was 25.6 meters tall. That's 84 feet, more than twice the height of the powerful waves surrounding it. The myth had just become a hard, scientific fact. This single measurement changed everything. It was not a sailor's memory, prone to fear and exaggeration. It was a cold, hard number printed out by a machine. The Dropner wave, as it came to be known, was the first official instrument-verified rogue wave ever recorded. The implications were profound. This one data point proved that the scientific community's understanding of the ocean was dangerously incomplete. It meant that the legends were true. It also meant that every ship at sea, every oil platform, every coastal defense system had been designed and built based on a fundamental misunderstanding of the ocean's true power. With the Dropner wave confirmed, the scientific search for an explanation began. The first and most intuitive theory was a phenomenon known as linear superposition. It's a straightforward idea. Imagine the ocean surface as a vast canvas of countless waves, all traveling in different directions. When 2 or more wave crests happen to meet at the same point, at the same time, their individual heights simply add together. This process is also called constructive interference. A 2-meter wave meeting another 2-meter wave creates a 4-meter wave. A 5-meter wave meeting a 3-meter wave creates an 8-meter peak. It's simple addition. The energy of each wave combines, creating a momentarily larger, more powerful surge before they continue on their separate paths, unchanged. To form a monster like the Dropner wave, this model required a perfect, fleeting alignment. Not just 2 waves, but a whole group of large waves would need to converge on a single point in the ocean, their crests synchronized with impossible precision. It would be the ultimate oceanic coincidence, a perfect storm of peaks. But when physicists and oceanographers calculated the odds, the linear model fell apart. The probability of such a perfect convergence was astronomically low. According to the math, a wave of that magnitude should be a 1 in 10,000 year event. Yet the data from ships and oil rigs suggested these giants appeared far more frequently. The simple explanation was too simple. It couldn't account for the raw, chaotic power that sailors had witnessed for centuries. The numbers didn't lie. Something was missing from the equation. The ocean was hiding a deeper, more complex secret. A different kind of physics was at play, one that went beyond simple addition and revealed a far more dynamic and unsettling reality. This led to a profound shift in thinking. Scientists began to explore the world of nonlinear dynamics. The old linear model assumed waves were independent entities, passing through each other like ghosts. The nonlinear view proposed something radically different. Waves are not independent. They interact. They influence one another, sometimes in dramatic and unpredictable ways. In a nonlinear system, the whole is not simply the sum of its parts. The presence of one large wave can fundamentally alter the behavior of the waves surrounding it. This new perspective suggested the ocean wasn't just a random collection of waves adding up. It was an interconnected web of energy, capable of concentrating its power in ways previously thought impossible. This wasn't just a minor adjustment to the theory. It was a complete paradigm shift. It meant that the formation of a rogue wave wasn't just a matter of luck or coincidence. It was a product of the ocean's own intricate internal physics, a system capable of generating its own monsters. And this led to the core revelation, a concept that sounds like something from mythology. It's a process called nonlinear focusing, but it can be thought of more simply as energy theft. Under the right conditions, a wave that is already slightly larger than its neighbors can begin to draw energy from the waves directly ahead of it and directly behind it. It acts like a lens, siphoning power from its surroundings. The energy from multiple smaller waves is funneled and compressed into a single, terrifyingly sharp peak. The wave doesn't just get taller by adding to others. It actively consumes their power, growing at an exponential rate, leaving smaller, weaker waves in its wake. This is how a wall of water can appear from a seemingly normal sea. This brought physicists to a powerful mathematical tool, one that originated in the world of quantum mechanics. It's called the nonlinear Schrödinger equation. This isn't just a formula. It is the language that describes how groups of waves evolve over time, and crucially, how they exchange and focus energy among themselves. The equation confirmed what the Draupner data suggested. The spontaneous growth of a monster wave was not a freak accident. It was a predictable, though rare, consequence of the laws of physics. The energy theft was real, mathematically proven, and embedded in the very nature of how waves interact on the open ocean. But this abstract physics needed a real-world trigger. Scientists discovered that certain ocean conditions dramatically increased the chances of these non-linear effects taking over. The most significant of these are powerful ocean currents that run in opposition to the direction of the waves. Think of the infamous Agulhas Current off the coast of South Africa. This powerful river of water flows against the massive waves rolling in from the Southern Ocean. The current compresses the wave field, shortening the distance between crests and forcing them closer together. This crowding effect acts like a lens, focusing the wave energy and creating a perfect breeding ground for rogue waves. With the how and why now understood, the scientific frontier has shifted to a new, urgent challenge. Prediction. We know rogue waves are possible, but can we ever forecast exactly when and where one will erupt from the sea? This is incredibly difficult. A rogue wave is a highly localized event. It can form and disappear in a matter of minutes. The new quest involves a global network of advanced tools. Satellites scan the ocean surface with radar, searching for telltale patterns in wave heights. Sophisticated buoys measure the sea state in real time, feeding data into powerful computer models. These models, driven by artificial intelligence, constantly analyze the ocean's energy, calculating the probability that a monster wave might be gathering its strength just over the horizon. This journey from maritime myth to proven science changes our entire perception of the sea. The rogue wave is no longer a ghost story whispered by sailors. It is a powerful, tangible symbol of the planet's deep complexity and a reminder of how much we still have to learn. It reveals that the ocean's surface is not a simple, chaotic system. It is a place governed by profound physical laws. These laws maintain a delicate balance most of the time, but can sometimes conspire to unleash a power that defies imagination, reminding us of the true, untamed nature of our world. The rogue wave was no longer a ghost story. It was a physical reality governed by complex mathematics, demanding a new respect for the ocean's power. The sea was not just a collection of predictable swells. It was a dynamic system capable of generating spontaneous, towering walls of water that could appear without warning and vanish just as quickly. This new understanding presents a monumental challenge. If these waves are a natural result of wave physics, can they be predicted? Scientists now use satellite data and buoys to scan the oceans, hunting for the specific conditions, the unique combination of wave trains and currents that are ripe for rogue wave formation. The goal is not just to see them, but to forecast them. However, the ocean surface is a place of immense complexity. Thousands of waves, all with different sizes, speeds, and directions, interact every second. This creates a chaotic environment where a small change in one area can have an enormous and unpredictable effect elsewhere. Predicting a single wave's emergence from this chaos is one of the toughest problems in modern oceanography. This means that, at any given moment, somewhere on the planet's vast oceans, a rogue wave is likely forming. Far from any shipping lane or sensor, a pocket of the sea is concentrating its energy, building a monster that will exist for less than a minute before collapsing back into the chaos that created it. Most of these events go completely unobserved by humanity. The implications for maritime engineering are profound. Ships are no longer designed just for the significant wave height, the average of the highest third of waves. They must now be built to withstand the statistical outlier, the 1 in 10,000 wave that defies all previous expectations of the sea's behavior. Modern ship designs incorporate reinforced hulls and new structural principles specifically to survive these extreme, instantaneous forces. The knowledge that a vertical wall of water could strike the vessel has fundamentally changed the blueprint for everything that travels on the open ocean, from massive container ships to offshore platforms. But the mystery deepens. If this phenomenon is based on the fundamental physics of waves, does it only happen in water? The mathematics suggested something more universal. The answer was a breathtaking revelation. It happens with light, too. In the field of optics, scientists have observed rogue light waves, intense, spontaneous pulses of light that emerge within fiber optic cables. They follow the same non-linear mathematics, stealing energy from surrounding light waves to create a brilliant, powerful, and short-lived flash. The same equation governs both a towering ocean wave and a pulse of light. This discovery reveals a fundamental principle of the universe. The tendency for energy to concentrate in chaotic wave systems is not unique to our oceans. It is a pattern that repeats across different physical domains, a hidden law of nature that connects the fury of the sea to the behavior of light itself. From a sailor's terrifying legend to a universal physical principle, the rogue wave has transformed our understanding. It reminds us that even in the 21st century, the planet holds profound secrets, and the ocean remains the ultimate arena for witnessing the raw, untamed, and deeply mathematical power of the natural world.